SAP Online Track session 213. If your SQL reads like assembler, you're doing it all wrong. This is a re-recording of the session that fixes some recording issues in the original recording. My name is Lars Breddemann, and this is me on the internet. I run a consulting company called Data Process Insights, where I work on databases, analytics, and SAP HANA topics. I also write a blog at lbreddemann.org, where I share my views and experiences with databases and especially with HANA. Let's start at the beginning. The idea and the promise of the information organization. The information that does not forget, that learns from the information collected over time. The way the technical realization of this idea is often shown is something like this. A central, mighty database fed by an all-important application which performs the business logic. All information are accessible in the central database. All consumers correctly understand the information and can use it immediately without any development effort besides setting up the pipeworks between the systems. But that's just mechanical data plumbing, cheap labor, if you will. It's a good world, this one. The sun of enlightenment goes up under the rainbow of knowledge exchange and growth. Happy days. Of course, we all know this is not at all how it is in real life. The actual situation most often looks like this, probably even a lot worse. There are many systems that are involved in performing business logic. Those systems use different interfaces to the database. The consumer systems turn out to also create new data that needs to be available to all the other systems. Yet every single system comes with its own way of providing data access or with their own limitations. As a consequence, custom interfaces are built between systems with different levels of data abstraction. It's not unusual to find multi-region, multi-cloud apps exchanging data with on-premise systems via CSV files. The well-curated information with context and meaning is reduced to the bare data elements with not even a technical consistency guarantee. This environment also leads to a situation where developers are used to work on those lowest levels of data analysis. With no better view on the data than the tables in the database, queries get written that not only should re-establish the business ideas, but that also should answer questions on the business level abstraction. As usual, when one tries to do many things at once, this does not often result in a great experience. Let's look at an example for that. This is a select statement from the SAP Community Q&A forum. It's not a ridiculously convoluted statement at all. In fact, this one is fairly tame in terms of nesting levels and mixing up of processing concerns. If I just highlight the output columns and the selection criteria, we can even get an idea what this query might be about. With customer name, balance due, and different timeframes, this sounds a lot like a financials query. Looking at the actual output, the purpose of the query immediately becomes clear. This is a customer aging report. The report is about invoice collection and can be used to estimate how likely a customer will pay the outstanding invoices. Yet nothing in the SQL code gave us an indication what the query really was about. The code spent all the mental capacity of the reader, us, on working on individual bits and pieces of the encoded data, and not on making clear what the domain question should be answered. This is a problem because it takes attention away from the purpose of the code and makes it hard to decide whether or not the domain question, in this case a financial question, has been answered at all, and if the result is correct. Without knowing and understanding the question to be answered, we cannot know if a given answer fits. Douglas Adams fans will recognize this as the deep thought problem. Today, I want to look into what led us, the developer industry, community, group of people working with databases, into this unfortunate situation. I'll take two different angles for that. First, what in the SQL language contributes to the situation, and then what factors does the developer or organization ecosystem add to that. The third and last part of this talk will then look at options for improving the situation. SQL databases have a rather interesting and often misunderstood property. They are schema on write databases. Developers who want to store any data in it need to first define the structure of the data. So they have to declare what columns and tables should be stored in the database and how these connect to each other. The way that developers do this is by modeling the domain and normalizing the tables. This is a way of defining how to encode domain information into the structure of the database. This means what we have in the database is encoded data, not the information in itself. In order to make the data useful again, it needs to be decoded again when it is read from the database. This is why SQL databases are meaning on read. Of course, this also applies to other databases like the NoSQL databases. With NoSQL, however, the developer first have to figure out the schema and then add the meaning. This separation between storing encoded or modeled data and recreating meaningful information is not accidental. In fact, it is one of the benefits of SQL databases. This way, we can compute new information from the stored data and are not bound by the structure the data was written into. There is no navigation required between records or documents, and the developer is typically completely shielded from the physical storage of the data. It's important to recognize that having the schema definition and the data entries is not sufficient to recreate the meaning of the data. This adding of meaning has to be done by the reader, the consumer of the data. And this is a step that often is forgotten or misunderstood. Just because the data is technically accessible, because I can select it from the tables, does not mean I know what it means. In my experience, this step of modeling a meaning for the reading of the data is heavily underestimated in many projects that deal with information exchange between systems, information analysis and intelligence, combining information from different systems, reusing information in new or changed processes. If you squint ever so slightly, you'll notice that this list practically covers all use cases for databases. In my eyes, this is a real problem everywhere you deal with databases. And there are more issues. The idea of writing data into a SQL database is to put in true statements of the model domain. This is nothing else than taking snapshots, static bits of information, and store them, encoded, into tables. Now, the thing is that the interesting information one typically wants to put in a database are not about anything static. The interesting information are about change that occurred or that may occur in the model domain. In financial systems, for example, the stored data, book entries, are about completed financial transactions, value changed ownership. Or in a weather database, the individual record is not interesting in itself, but put together, changes and the dynamics driving those changes can be analyzed and may be understood. Despite all of this, SQL databases don't provide many built-in options or standards on how to best encode data about change. Another gap related to the schema on write, meaning on read idea from the previous slide is that all the data modeling laws and tools focus on storing data and on avoiding problems with the technology. This might be due to the time and circumstances present when the relational SQL concepts were developed. Most systems back then had to roll their own low-level data storage logic. So the existing tools help to avoid things like lost writes, data duplication, or phantom reads, but there is little to guide the consumer of the data. In fact, reads of the data can be arbitrary, and all the database constraints only cover on what can be stored in it, but not what kind of reads make sense. For example, think about how it can make sense to join a customer email addresses table with a factory calendar table. There is no obvious correct answer for that. The consumer of this join needs to define the meaning of the result. Last but not least, SQL does not make it easy to get familiar with the real SQL. While it is standardized, the standard documents are not freely available. One has to pay for getting access to the current documents. And even with this access, the documents are a tough read. Nearly 3,800 pages of dense formal language definition. This is not aimed at the SQL user, but at the developers that build SQL database management systems. And while every database nowadays speaks SQL, the lingua franca of the databases, every database does that in its own dialect. That's not very helpful. The aim for compatibility here is often a race to the bottom in terms of supported functions and features. In many cases, the majority follows what the big players do, which sort of establishes an informal standard. If you want your new database system to get users, it better works with the commands that work on MySQL, Oracle, or SQL Server. Now, this was about the SQL language and its contribution to the situation. Let's look at the developer and organizations complex next. I see this complex split into 4 separate aspects. SQL training is the first one. While SQL training has become a lot more available in the last 20 years, starting with the internet explosion between 1995 and 2000, the contents of those trainings remained pretty much the same. Typically, the material has an extreme focus on syntax and commands, trying to cover all the different functions and expressions one could use. The example problems are often simplistic, and the right solution is nearly always presented as a single select command. Anything more complex is commonly used to motivate the use of procedural code. What isn't covered a lot is the intention of language features and how they are used in real life. Like any other language, SQL is full of additions and changes to it based on how people use it. Commands like merge and upsert, or features like XML in the database, were introduced to support very specific scenarios. Yet the SQL trainings don't explain those scenarios. Today, it's JSON in the database, and in some years, new users of SQL will have to figure out for themselves when to use or not to use this feature. This is not an arbitrary point I'm trying to make here. The unconscious fixation on answering domain questions with a single query or a single view or model is very much present in customer projects. Look at this dashboard, for example. This dashboard answers many different questions at once. It looks at different data in the database from multiple angles and translates it into several domain-level concepts, like types of income versus expenses, income trends, and so forth. It should be obvious that this probably is not best handled in a single SQL command or view. Obviously, these questions have many things in common. For example, the same reference time frame and a shared definition of how to decode costs and income from the database tables. But that does not mean that all answers need to come out of a single statement. Yet, this is rarely covered in SQL or database tutorials. It's a bit like learning a foreign language and never being shown any prose written in that language. While all syntax, grammar, and vocabulary is covered, one is not likely going to write any meaningful text anytime soon with that. But it's not only the training that shapes the thinking about how SQL programs should look like and how to answer questions with SQL. In most organizations, there exists a strong bias towards the existing systems, towards the legacy systems. These represent the status quo and what naturally indicated the way to go for the developers, for the project teams, and the managers. Typically, developers working on business systems are shielded from having to deal with the database directly by using frameworks. ABAP is such a framework, and while OpenSQL looks a lot like SQL, it encourages a getter-setter style of interacting with the database, which of course is what prominent developers like Fowler or Bob Martin advocate to keep applications DB agnostic. The downside of this approach is that it does not foster the push down of computations to the DB level. This is probably one of the more challenging points in this context. Computation is often taken as the same as business logic, and business logic should stay in the application. It's pretty much the reason to exist for the application. The point here is that business logic really is about the rules in terms of the domain. It's not about decoding data from the database. As this distinction is not too obvious, many developers may feel like they should keep control of the whole package of DB decoder and business logic. In effect, this also means that the application developers control the access to the information. Coming back to the use of frameworks, in many cases the database framework hides complex data access patterns from the developer to the point that the developer is not even aware of it. It is a bit like driving a car with ABS and automatic shifting. The driver of such a car does usually not know how and when the car changes gears or engages or releases the brakes. I've got a few examples for such complex data access pattern on the next slide. There are cluster or pool tables that store several ABAP tables in one or few database tables. This is done to save joins and or application database network round trips. We find different approaches to keeping history of data changes. And there's different ways to store hierarchy information and different approaches to store information about money. Whatever you do, don't use floating point. And of course, there's the ever popular flexible dynamic key value store table, also known as the one table to rule them all. Just don't. While this is just a brief selection of such patterns, it's worthwhile to note that these are only concerned with data decoding. None of those patterns is about getting meaningful information. The next part in the developer organizations complex is tooling support. Nearly all database SQL-oriented tools focus on syntax support, both as text and as a graphical representation of it. There's barely any tools that understand how a data model belongs together and that helps with developing meaningful programs. Most of the tools don't even recognize the access patterns mentioned before. That means, for example, the data scientist or analytics developer not only has to figure out how to model a specific domain question with the data stored in the database, this poor person also has to waste lifetime on re-implementing data access patterns in the SQL commands to get the data from the database in the right way. Then there are obvious lacks, such as the lack of linters that would standardize SQL code and automate formatting across teams and projects. I don't know how much time I've wasted by just making SQL readable in some way by adding line breaks, indentation, and whitespace. Of course, there are programs available to do such things, but those are not available everywhere and not the default, like we have defaults in JavaScript, Python, and yes, also in ABAP. Finally, in this section, the tools that are more concerned with the meaning of the data modeling tools like Irwin or Power Designer, are commonly thought to be for architects only. This is probably one of the remnants from the glory days of case tools in the 1990s. Back then, the idea of model-driven development was popular, and the hopeless support of round-trip development stopped it in its track. Database development approaches like agile and software craftsmanship are very much in opposition to the top-down method because of its negative impact on development progress. The last quadrant in this diagram is about database technology and how databases are used in organizations. The database technology progress of the past decades mostly focused on operational topics. Features like index and tuning advisors, compression, or database in the cloud exist to make it cheaper to use a database. In contrast, there are barely any features that help with getting better information or asking better questions or modeling better points of view on the data. This focus on operational costs goes hand in hand with the notion that the value of a database is a function of the data volume it manages. Big must be important and contain a lot of meaning to the organization. This oversimplification is then also found in the assumed ease with which data in a SQL database can be used. Somehow the sunrise rainbow idea prevails in the heads of some architects, project leads, and decision makers in the organization. Otherwise, some estimations for data integration projects could not be explained. To leave this slide with a summary, I believe it's fair to say that the SQL databases are commonly oversimplified in how they are used as development tools. The training leaves out important but more complex topics. Developers shield themselves from dealing with those topics. Tools are stuck at the lowest level of support for developers, and decision makers assume a simple ideal world that there never is. No wonder most people really struggle when trying to do something non-trivial with databases. So better let's have a look at some options on how to improve that. When thinking about what could possibly be done by an individual developer, I think the range of options looks a bit like this. On the one hand, we find NoSQL and data lakes. This approach basically means leave the problem to the next poor schmuck that has to work with the collected data. Slight improvement might be to have a shared catalog of data definitions and conventions. That's something, but not all that much. On the other hand, we find the already mentioned strong top-down semantic modeling approaches. Think case tools, service-oriented architecture, and semantic web. All that is required to make this work is to get the whole organization and all its communication partners, basically the world, to agree on an approach. We've seen that fail a couple of times around. This leaves us the middle ground. Options that both add meaning to code and that don't require the approval and agreement of the whole world. That means writing structured and readable SQL code. It means writing functional SQL code, composable elements similar to functional programming. It means having domain names in the SQL code, also known as literate SQL, and to be explicit about the meaning of the code. With explicit meaning, I mean to say, don't try and be flexible and dynamic in SQL code. SQL is a static language, and SQL databases have a hard time optimizing dynamic code well. In most cases, there is not even need for dynamic SQL. If the generalization of functionality really is useful, just write a SQL query generator in the application. That's the best place to keep the knowledge of how your application or decodes data as an access pattern. Don't build a framework in your SQL code. Now, of course, when asking a question, that is, when writing a SQL query, make it about one domain concept. Don't complex multiple topics into a single query. This is well-meant advice based on my personal experience during the last 20 or so years of working with databases. But how can you put that into practice? One mental model that I found helpful is to split up queries into different stages of processing. Starting from the left, we have the data as it is stored in the database. To make any sense of that, we need to decode, reassemble, join, and map it. If required, we also need to follow the access patterns of the application or the framework that initially wrote the data. For example, find the current valid record from a table with the whole record history of all records. Once this is done, we can re-establish domain information. As said before, this information will likely be about change of one thing or the other. So there will likely be things like time references and expressions about the speed of change as part of the query. As these concepts themselves can be complex and counterintuitive, it is really important to try and treat them separately from the data encoding. At this stage, we can also compute new information and new facts from the existing data. Finally, we can answer domain questions about the information and the data. This, of course, is not a prescription to chop up any SQL into 4 parts, but rather a mental rail to organize the necessary work. And like all development work, it is not a straight progression from one stage to the next, but a repeated back and forth circling between these aspects. To make it more concrete, I'll finish this talk with a few examples for how this approach can be put into practice. I've taken the customer aging report from the beginning and refactored it into something that delivers the same result, but it's much easier to read and understand. One often or underused feature of SQL is the common table expression or with clause. These are nothing but named subqueries that can be used like normal tables or views in the SQL that follows. It's perfectly fine to refer to common table expressions or CTEs in CTEs as long as the definition is done before the reference to the CTE is made. That is to say, if you read this statement from top to bottom, you can use any CTE for which you have already read the definition. With the right text editor, the implementation code for the CTEs can be folded away and we see the names and signatures. This is what the data looks like that the CTE returns with a final query. This final query is now obviously about customer aging and spells out the names of the elements in domain terms and not database column abbreviations. As a developer, I can open or close the folded CTEs and focus my understanding and/or my changes just on the piece of code of this one piece of code. This makes comprehending a lot easier than trying to cram the whole statement into your brain at the same time. This separation of concerns in the code also allows for easy refactoring of it. Look at the implementation for customer credit debits range text. We see that I've used a lookup table named due days text that is joined with the data from the previous CTE. Now, maybe I'm not too happy about this approach. Maybe I don't want another join and I'm happy to have the definition of the ranges in the statement itself. With a code structured like this, it's trivial to swap out one implementation for another without impacting the remaining statement. As long as the signature of the CTE remains unchanged, I don't have to worry about any other parts of the code. This is similar to functional programming. This also means I can easily check parts of the statement logic and replace it with mocks. A create table as can be used to materialize the computation of the statement up to the CTE you want to mock out. And then all you need to do is to select from the mock table instead of the actual data. This can come in handy when trying to check the impact to runtime and resource consumption of the parts of the statement that use the mock data. The with clause technique also allows to turn the statement local views into commonly shared views easily. Again, this takes minimal effort, and in the consuming statements, I can then simply remove the CTE that the view replaces. Another example for how to structure SQL code is an implementation of the ABAP special access pattern implicit default values. ABAP provides the nice feature where a developer can say, give me the detail information for this list of items, and if an item does not have specific detail information, then give me the default in item back. I recently learned about this pattern based on a blog post by Paul Hardy. For a more complete write-up, make sure to check my blog, Find the One or the Other, on lbreddemann.org. For now, just understand that this feature is implemented in ABAP by always storing a designated default value in the details table. In this example here, the detail information are payment terms. The default values are marked by a special magic item number 00000, which is the ABAP initial value, another ABAP framework concept that does not exist in SQL databases. Now, to resolve this with a SQL statement, this access pattern needs to be followed. Imagine a data scientist that should analyze the data and consider the payment terms. A simple join won't get the right result. By encapsulating this access pattern into a view, the data scientist can use it as if it was a simple table and does not need to care about the implementation detail. The caveat is that one should not try to be smart about implementing the access pattern dynamically so that the implementation would cover all occurrences of it across the database. This would lead to code that is hard to understand and hard to maintain. While the DRY principle, don't repeat yourself, calls for a single unambiguous authoritative representation within a system, it talks about pieces of knowledge. And the piece of knowledge in this statement deals with item and payment terms, not the implementation of the access pattern. It is much easier to understand the access pattern and implement it again for other pieces of knowledge than to try and rebuild the framework in SQL. As mentioned, there are actually a number of different techniques that can be used to make SQL code easier to write, read, understand, and maintain. Things like views on views, which SAP calls them layered views and markets them as a virtual data model can help a lot here. Stackable or composable table functions can really be helpful when there in fact is a general aspect of a query that should be implemented only once. We'll look into an example for that in the next slide. Overall, however, it's advisable to defer generalization as long as possible. If your code really should support many different ways to define queries and run them, your specification asks for a query engine. That's what all the reporting front ends and data warehouses do. They all generate specific SQL commands from the input specifications of the user. It's a lot easier that way around, since you can use tools and options of your development language. Especially string processing is much stronger in Java, Python, C, etc. than it is in SQL. The promised example for stackable or composable table functions is this. Here we have a simple schema with sales in a customer table. Now, to implement the concept of an active customer, what we can do is to write a table function that takes a set of customers represented by their IDs, cost ID, perform a computation and return a set of active customers. In this example, I decided that an active customer is one that has bought something in the last 60 days, so I implemented this in a subquery in my table function. How exactly this part works is not really the point though. What's important here is that this table function can be fed with any set of customer IDs and will always return those from the set that are active customers according to this one single definition. This is effectively a business rule that I define once and that I can reuse in any other code where I need it. And this it is. A quick tour through what makes the SQL world challenging and uncomfortable and what we can do to make it a bit better for us and others. By being aware of the complexities that are embedded into real-life landscapes, you're hopefully better prepared to what is required to get meaningful information from your databases. Now you can get back on your diner again and right into the sunset. Thanks for your attention and patience, and a big thank you to the organizers and volunteers that made this SAP Online Track possible. Cheers, Lars.